taking time out of your day, first of all, and allowing us the opportunity to present to you guys. Really appreciate it. As Joe said, Hurricane Paloma's rapidly intense weekend. I'll be covering November 7th to the 9th, 2008. A little background information on Paloma. It was, of the 2008 season, 17th tropical storm, 17th tropical cyclone, 16th tropical storm, 8th hurricane, and the 5th major hurricane. Entire lifetime lasted from the 5th to the 10th. It was the 3rd strongest November Atlantic hurricane on record, and the name Paloma has officially been retired due to the damage it did in Cuba. This afternoon's topic of conversation, the factors contributing to Paloma's rapid intensification, which I found were the relatively warm sea surface temperatures and low shear, and contributing to rapid weakening. Cool sea surface temperatures on the opposite side of Cuba, Cuba's topography, high shear environment, and an encounter with dry air. My next slide is a quick YouTube video just of Paloma's life cycle. I'm going to click on the link because we couldn't get the video to work yesterday here. But when watching this video, keep in mind any questions you might have as to why any of this is going on, and I will hopefully be able to answer some of the questions you guys have. Once again, the storage fact, which in and of itself is a little unusual. And then we can start to see the genesis of what is now tropical cyclone Paloma, which intensified to a tropical storm, and then to a hurricane. A couple of times I wanted to pause this. Right about here, we can see high cloud tops. How does this laser pointer work?
The top button.
Top button?
Mm-hmm.
I'm partially colorblind, so. High cloud tops over here are showing good outflow. What that basically means is the hurricane is breathing well. It's taking in warm air and it's expelling the warm air from the center of circulation outward, which allows for more warm air to circulate inward towards the center. But you can see this outflow pop up a few times during the life cycle here. When you see the high clouds expelling outward. Right about here is rapid intensification. We can see the eye wall forming. Paloma makes landfall, and then we can see she pretty much disappears off of the map. Very quickly weakens as well. Little patience here. Okay, rapid intensification. The circle area right there, this is a sea surface temperature map image. In 24 hours, Paloma's pressure dropped 38 millibars and the winds increased 45 knots from 86 miles an hour to 138 miles an hour. The circle right there that I noted out is extremely warm sea surface temperature. There's even a spot there which could be warmer than 32 degrees Celsius, which is 89 degrees Fahrenheit, which is extremely warm water. Here is Friday. I don't know if any of you guys are into professional golf, but Friday is referred to as moving day. It's when the golfers try and shoot their best score to make the weekend to hopefully win the tournament. And I think Paloma definitely noted that. I think Friday was definitely her moving day. This is the beginning of her rapid intensification. And one of the things I wanted to point out here, Margie, who was a graduate student here who gave us a presentation, showed us some of the things from this 37 gigahertz color enhancement. In other images, this is a visible image, an infrared image on top. You can't see an eye wall or an eye very well at all. But if we look at this 37 gigahertz image, we can see a very well deformed eye wall. The color there, the cyan color, is high cloud tops, which denotes ice. And we can see that circulation and all of this heavy convection around the center of the storm, which is a very good indicator that a storm is intensified. Here's a composite image of Friday, November 7th. And when we're looking at these images, we're starting to see an eye wall form. And the deep convection, as I said, is near the center of the storm, which is very good. It's in a low shear environment. Here's the next day. With these images, we can now see a well-deformed eye with Plenty of cold cloud tops on fully around the surface, and the deep convection is still on the storm. I can flip a little back and forth. You guys can see the difference between Friday and Saturday there. Very well deformed eye on Saturday. When we're looking at these images, the image on the left is a wind shear analysis map. Yellow lines follow contours of similar shear and magnitude, and the pink lines with the arrows show the direction. I wanted to point that out because we can see in the image that Paloma is in a relatively low area of shear here on Saturday, but if she continues to track any more north, we can see where there's 30, 40 knots of shear. So you can almost predict that it's going to intensify, or weaken, I'm sorry. Factors contributing to the weakening. Especially considering the south side of Cuba, the north side of Cuba has really cool water compared to the south side. 24 hours after her most intense point, shear pressure increased 50 millibars and the winds decreased almost 70 miles an hour. As I said, the cool water on the north was a big factor in that white area, as Andres actually pointed out, is upwelling due to the storm. The storm sucks in the warm moisture from the bottom, causes cool water from underneath to replace it, which causes upwelling. Another factor in weakening is the mountainous regions right in between where Paloma made landfall. What that does is the lower level circulation that helps maintain Paloma's intensity diminished significantly. Here's a water vapor image. This is during strongest intensity. Paloma's surviving very well here, but we can see pockets of dry air almost, in each little quadrant. Northwest, southwest, northeast, southeast, which isn't a factor right now, but we'll see will start becoming a factor. As Paloma moves north, she's encountering more shear. The shear is kind of producing a double whammy in knocking the deep convection away from the center and allowing dry air to enter the surface. And here's two more images. We can see I had to circle the center of circulation, and if we were just going off this water vapor model, we probably wouldn't be able to find where the center of circulation is. All the deep convection is well east of the center of circulation, and by this last image, which I believe is on Monday, almost all the convection is northeast, and you would not be able to tell that there's a center of circulation and low pressure there just by this image. Here's a photo of Monday, just to reiterate the fact. I also want to show on the wind shear map. The wind shear also has an infrared layer where we can see, if I can find this laser, there we go. That area right there, you can't see this low level circulation right here, right above Cuba on this infrared map because it only captures cold temperatures of cold cloud tops. So looking at this image, this infrared image, you might assume that there's a center somewhere over here, just looking at the image. But to look at different images, which is a lot of things we learned on this internship, don't assume one thing off of one image. Get a lot of ideas off different images. Circle that there. Here's a composite photo of the 10th, which was Monday. And we can see convection once again sheared off. There's dry air in the center. There's nothing impressive looking on the microwave images. My references, and I just wanted to say thank you to everybody who had a part of the internship. Definitely learned a lot, and I really look forward to working with everybody hopefully soon in the future. And that's